In this example, we are going to have air that is at a pressure of 600 kilopascal and a temperature of 330 kelvins. It's going to enter a well-insulated horizontal pipe having a diameter of 1.2 centimeters, and it exits at a pressure of 120 kilopascal and 300 Kelvin. We're going to apply the ideal gas model for air, and we're going to determine at steady state the inlet and exit velocities and the mass flow rate. Now, before we get started, let's make sure we know all of the keywords. It says well insulated. That typically means we don't have to worry about any energy transfer due to heat. We've got diameters of the pipe, or one diameter, it's 1.2 centimeters. And we also know we have an ideal gas model. And we're determining at steady state. All right, so these three things right here are going to be important to realize. Now let's go ahead, and I always like to draw a picture for the problems where one is not given. So here's the inlet. We'll say point 2 is over here, as that's going to be the exit. So we've got mass flowing in here. The temperature is 600 kilopascal. Temperature is 330 Kelvin. At the exit, we've got 120 kilopascal for pressure, and the temperature is 300 Kelvin. This diameter is 1.2 centimeters. Now we want to find inlet and exit velocities. So for part A, we're wanting V1 and V2. That's what we are looking for. We are at steady state. So since we are at steady state, we know that we can write that M1 dot equals M2 dot. Now if we use our equations for mass flow rate, we can write that rho 1 A1 V1 has to equal rho 2 A2 V2. Now we want to find V1. So let's look at this equation and let's solve this for V1. Let me do that on this next page. Alright, so if we go ahead and we solve this equation for V1, we're going to get that V1 equals rho 2 A2 V2 over rho 1 A1. Now what about the areas? Do we have to keep both of those in there? Nope, because those are going to be the same, right? We only have one diameter, so those will cancel out. Now we've got this. Now we were also told we have an ideal gas model. Remember that you can write out your equation that pressure equals rho RT for the ideal gas model. So we can use this equation. Now we've got density in here. We aren't given anything about density, so let's try to get rid of that. We're going to get rid of that by using this equation. So let's solve this for density, and we will get pressure over RT. Now let's plug this into this equation. If we do that, we get P2 over R times T2 times your velocity V2. That's going to be over P1 over R times T1. Now if you go through, get rid of the fraction here on the bottom, kind of simplify it a little bit, you're going to get that V1 equals P2 over P1 times T1 over T2 times V2. Let's plug in our values. P2 is 120 kilopascal. P1 is 600 kilopascal. Our temperature, we're going to have 330 Kelvin over 300 Kelvin multiplied by V2. Now this, we can simplify, and this allows us to get the relationship between V1 and V2. So the velocity at the inlet is going to be 0.22 times V2. So it's 22% of the exit velocity. We'll hang on to this and we'll use it in just a second. We still don't have enough to solve because we have two unknowns still. Now let's go ahead and go to our energy balance equation. We're going to be using that long energy balance equation because now we've got mass flow, so we have to account for the energy brought about from that mass flow. So our equation is going to be 0 equals QCV dot minus WCV dot plus M dot, because remember M1 dot equals M2 dot, so let's just replace it with M dot. Multiply that by H1 minus H2 times V1 squared minus V2 squared, put that over 2, plus G times Z1 minus Z2. So that's our equation. Now let's look at that and see if we can simplify any of this. First of all, the potential term. Do we have any change in elevation? Nope. Let's get rid of that. We don't need that in there. Over here, do we have any rate of heat transfer due, well, any rate of energy transfer due to heat? Nope, because we said it was well insulated, so that goes away. WCV dot, do we have any sort of external rotating shafts or electrical power or anything like that? Nope, goes to 0. Now we've simplified our equation quite a bit. So let's go ahead and look at this new simplified equation. We're going to have 0 equals M dot times H1 minus H2 plus, now we get to this kinetic term. Notice we have V1 here. Let's plug that equation in. So we're going to have plus 0.22 V2, square that, then subtract V2 squared, put that over 2. Okay, so now we've got that equation. So that looks good. Now let's see what we can do after that. First thing we should notice is we've got this left-hand side, which is 0. Now we can divide through both sides of this equation by M dot. And if we do that, that goes away, this goes to 0. Okay, so that kind of gets rid of that M dot in the equation. Okay, so keep that in mind. Next we have the difference in enthalpy. Now this is going to come from the table. We have an ideal gas, so you're going to use the ideal gas table, which is table A22. Now if we go to that table and we use our temperatures, pressures that we have, actually we don't need pressure, we just need temperature. This is what the table looks like. Remember, we are at a temperature of 330 Kelvin. So H at 330 Kelvin is going to be 330.34. So let's write that number down. And that's kilojoules per kilogram. We do the same thing at H2. So there, the temperature is 300. So at 300, we have 300.19. So we write that number down. Okay, so now that we have that, we can plug these two numbers into our equation, and then we'll see if we are able to solve for anything. So 0 is going to be 330.34 minus 300.19. That's kilojoule per kilogram. I want to get this in joules. So we want 1,000 joules per 1 kilogram or kilojoule. And then we're going to subtract this right here. So if you simplify this, you're going to get 0.9516 V2 squared. That's still over 2. So now you can solve for V2. And V2 is going to give you 251.73 meters per second. So now we were able to solve for velocity at the exit. So that is good. All right. And how will we now get velocity at the inlet? That's right. We're just going to go up to this equation again. So V1 is just going to be 22% of this. So just multiply that number by 0.22. And you get 55.38 meters per second. So that'll be your velocity at the inlet. So far so good, right? So now we gotta go to point B, or not point B, but part B. And this one we want to find mass flow rate. So we're looking for m dot. Let's write down our equation for m dot. Rho AV. Remember, rho we can find using the ideal gas model. So we're going to have pressure over RT. We have a pressure, we have a temperature, we can find R. So that means we can get density. Numbers here, we're going to have 600 kilopascal. And we need to do some conversions here. We're going to switch it over to pascals first. Then let's go to newtons per square meter. So that'll be the numerator. And then we're going to put that over R times T. So we got the 8314 number, and then put that over 28.97. That's going to be Newton meters per kilogram Kelvin. Multiply that by the temperature. That's already in kelvins, so we don't have to convert there. Now we've got all of the units that we need. So notice all of this cancels out. What you are left with will be kilogram per cubic meter. So density is now going to be 6.335 kilogram per cubic meter. All right, perfect. Now that we have this, we can plug it into this equation. So m dot is going to be 6.335 kilogram per cubic meter. We're going to multiply that by area. We have the diameter. And the diameter was given in centimeters. We need to convert that over to meters because we have meters right here. So after you do the conversion, when you find the area, you're going to get pi times 0.012 divided by 2. Square that. Multiply that by velocity. And our velocity at that exit is 55.38 meters per second. So our mass flow rate is going to be 0.0397 kilograms per second. Alright guys, so that's how you'd go about solving that problem. As you can see, they are getting a little longer just because our equations are longer now. But they're still not too bad, hopefully. Alright, see you on the next video.